Let's talk a little bit about Laplace transforms. So a Laplace transform is more or less a linear operator. This allows you to perform forward transformations into the Laplace space from your time space, and you can also perform an inverse transformation back into your time space from your Laplace space. Now, what this is really doing is allowing you to solve ODEs much more simply. And also, we have a table essentially of how to solve based on different types of input functions. So you don't necessarily need to memorize any of this, but you do need to know how to actually work with it and use Laplace as a way of solving these types of differential equations that you'll come across in this course. So in the forward Laplace transform, what we're seeing here is that the Laplace taken on f of t is equal to f of s, meaning it's now in Laplace space. This is based on the integration of the left-hand side of 0 to infinity for your f of t function multiplied by this new e to the negative st dt. And ultimately, this type of expression for performing your Laplace transform is based on any type of function of f of t. And this is where truly we do use those tables where if f of t is a step function or if it's based on a derivative, we have a discrete solution that's already solved for us that we can use. But the purpose of this part of the lecture is to actually walk you through a little bit more about the actual operation mathematically so that it makes more sense to us and is a little bit more intuitive. So what makes the Laplace space S so interesting is that it's able to combine complex variables of the real function A, which is just saying all the real values that are in the Laplace space, and the imaginary values in B, so the imaginary values that are present in the Laplace space. We can think of this as a real versus imaginary axis, where we can actually have any point in space that is described using this type of equation. Now, it's S equals A plus B times I in the Cartesian coordinate space, where I is your imaginary number, where I squared is equal to -1, or I is equal to the square root of -1. In polar coordinates, we can also describe this using the Laplace space value S, which is equal to its real value, which is the square root of a squared plus b squared to get your radius, e to the phi I, where phi is the inverse tangent of b over a, which are based on those two values too. And again, this is based on you having a present value of, say, you have your imaginary space and your real space, and maybe you have some point value here, and you're trying to determine ultimately what is happening in the real versus what's happening in the imaginary. So real happening here, imaginary is happening here. We could describe those directly as A and B, but in doing so, we can also think of it as, well, we might be in a polar space where we might need to consider directly what is the radius, and then from there, what is the angle to get to there, or v. So in considering this between our Cartesian coordinate spaces, we know that we can describe any potential value in our Laplace space as we go through these transforms. We can also do an inverse transform on this operation, which takes us back to f of t, where we use this inverse Laplace L to the -1 of the function f of s. This, though, can only be done for times that are greater than or equal to 0, which is an important distinction. We can use a principle of superposition, which allows us to take Laplace of a more complex function, like a x of t plus b y of t. In the previous one, we can consider that where maybe x of t is our temperature and y of t is our q. And we can say, essentially, we can pull out those constant values, where constant value here is just a 1 in front of t, or a -1 truly. And b would be of kp. So we can pull those out before performing the Laplace. Then we could perform that on x of t, in this case temperature, or y of t, in this case q, and we would get a times our new Laplace x of s plus b of y of s, where these are based on the potential inputs of what those might have, which could be, again, step functions, impulses, derivatives. It is endless, but it's a really fantastic way of allowing us to solve more complex ODEs actually a lot more quickly. And it gets really valuable when we move into more complex systems, when we move on to the next sections on like transfer functions. So this is a description of what a Laplace is and how we can potentially use it. So there's a couple of examples that we can walk through. And my goal of keeping this here is that this is a tangible example of what we can move back to. And we're going to use Laplace transforms to ultimately solve this ODE. And while we've previously solved it to become this, we're going to show that both ways actually yield the same function. So let's consider a few examples of interest. The first example we're going to have is a step function. Now, we described step functions as a way of simulating what's happening in this system as we have a step function increase of q, our manipulated variable, and we kept our disturbance variable ti constant, so we are going to be using this as a unique example. What's happening with a step function ultimately is that if we describe some value, and let's call our function f of t, this could be equal to 0 for values of t that's less than 0, or 1 if t is greater than or equal to 0. And this is just saying again that we're moving up from 0 to 1, where this is our function f and this is time. That's the step value. The difference is equal to 1. We are just simply describing its step function up at any given endpoint, where this is t equals 0 itself. 0 looks very bad, sorry. So how would we describe this and how would we perform the Laplace transform on this function f of t? So let's take the Laplace of f of t, which is going to be the Laplace of essentially our function here described right here. To do that, we are going to take on this side the integral of our function from 0 to the left side to infinity of f of t e to the negative s t dt. And now when we consider this, we have two potential values that we're actually looking at if we go ahead and consider the integration on both of these equally. So we can describe this as what is actually happening from 0 of the left-hand side, so that means really over here, to 0 itself on the right-hand side. And that is actually performed, that positive looks very bad, I'm sorry. My handwriting is not the best, but I'm working on it. That describes the first part here, where f of t itself is 0 times e to the negative st dt. And this now can be added to the other segment of our total time. And really what I've done is I've just split up the time to describe the two parts of the step function, on the left-hand side and on the right-hand side. And now this will be from 0 on the right-hand side into infinity, which all of that is equal to 1. So now that's just 1 e to the negative st dt. Now this 0 is automatically going to turn this entire function into 0, meaning that now we can look at just this part of the equation, which is the integral of 0 on the right-hand side to infinity, where that value will always be equal to 1. That's going to be multiplied by e to the negative st dt. The 1 can be pulled out of the expression, and we can do the integration on e to the negative st. That is negative 1 over s times e to the negative st from 0 positive to infinity. That 0 positive is just 0. It's just describing where on the 0 it is, which is the right-hand side. With that, that's negative 1 over s times e to the negative s times infinity minus e to the negative s times 0. E to the negative s infinity is just e to the negative infinity, and we know that e to the negative infinity is equal to 0. E to the negative 0, anything to the 0, in that sense anyways, is going to be 1. E to negative 0 is 1. Therefore, this is going to be negative 1 over s times negative 1. This is equal to 1 over s. Thus, the step function, a Laplace of a step function itself, is just equal to 1 over s. And I'm going to guess that that means if we take the inverse Laplace to get back to f of t of our function f of s, which is inverse Laplace of now 1 over s, that should theoretically go back to become back to what we originally had, which is f of t, where in this case, if it's on that right-hand side, is going to be equal to 1. Now, why is that part important? Remember, the inverse Laplace transform has to be for t that's greater than or equal to 0. And in that case, our condition is that it's equal to 1. We're not going to be able to consider what happens beforehand. We can only consider that point forward. Thus, that is why our inverse Laplace of this specific step function goes back to whatever the value was at the greater than or equal to 0, which is 1. But let's say that this entire time, instead of 1, we had a value of, we'll call it x. that entire time, we would have had the ability to pull x out of the expression. That would become the integration here that has an x, and that would still remain x all the way through, meaning that we would have f of t be x. Now, for simplicity, I chose x because t would look a little bit too confusing, but I chose x because it looked basically the same as a 1. Now, that describes our step function. I'm going to do a little bit of rearranging so that we could describe a more unique expression like a derivative operator, and afterwards, we're going to go ahead and re-express this value. We're now going to do a derivative operator. Now, this is going to throw us back a little bit to calculus 1 and 2. So let's consider the ability to do the linear operation on derivatives for, let's take df dt, where f is a function of t. Let's perform a Laplace transform on that, which would then become 0 from the negative side to infinity of f of t, where our f of t term is now df dt itself, e to the negative st dt. And this really is just the operator that we're looking at. Now before, we used a step function, but now this is more of a continuous function that we could describe. What's really going to be interesting about this is in order to solve this, we need to think about our chain rule in the inverse space. We want to consider, remember, u dv equals uv minus v du. So u dv equals uv minus v du that we all used in calculus. We're going to take that to match this expression here. So what is the u and what is the dv? Let's break that up into our component pieces. Let's take our u and describe it as that. So in order to do that, I'll add a little bit of color. And then let's take our dv term to become this one, because if we multiply dt by dt, we get df. So that'll be our dv component. Let's first look at the dv component, because in my brain, that's always the one that's faster. So dv is more or less equal to df dt dt. Well, that makes sense, because in reality, we're really just saying that that's df itself. And thus, dv is equal to df, meaning v equals f. That one was pretty fast to solve. The other component is going to be our u term. And so we've just found dv and v. U is equal to e to the negative st. Thus, if we took the derivative of that term to get a du, that would then become du is equal to negative s e to the negative st. And that is going to need to be multiplied by, you guessed it, dt. Because u is a function technically now of s, and we are trying to determine what's really happening here in this condition. So in that mindset, we are considering the approximate value that we are looking into this expression. We are taking dv, v, u, and du to redefine this expression here. Originally, we have this as the integral of u dv, so let's rewrite this as uv minus the integral of v du. So in order to do that, we're going to pull this expression back down, and this is going to be equal to same integral sides, but u and v specifically already integrated for that term. So u was e to the negative st, and v is f of t. From 0 on the negative to infinity. We're going to go ahead and subtract the integral from 0 negative to infinity of v, which is f of t, times du. Now, du is going to be that negative s e to the negative st dt term. And that means we have our dt term back in here, and we have f times e to negative st. Now, funny enough, we know how to solve that one pretty well by now. We just did it in the last example, and in this case, because s is inherent to this, we can pull the s part out. And so when we solve this first expression, this is going to be e to the negative infinity times f of infinity minus e to the negative s times 0 times f of 0. Minus, we can pull the s term out, and we're going to be doing negative of negative. So we're adding s times the integral of 0 to the negative f of t e to the negative st dt. Now this is the definition of our Laplace transform, like to a t the definition. Here, e to the negative infinity is going to be 0. E to the negative 0 is going to be 1, as we've described. So on this portion, this is going to become 0 times f of infinity, or 0, minus 1 times f of 0 on specifically the left-hand side, and that will become f of 0 to the right-hand side. This then is going to be added to s multiplied by this term expression is the definition of our Laplace transform. And so this term specifically is f of s. As we've described previously, that is the technical definition function of the forward Laplace transform. And now we can see directly that this integral, when we really pull it back down onto the bottom of our screen here, Laplace of df dt is going to be equal to s times f of s minus, so sorry, I forgot that minus from before, f of 0 from the left-hand side. And how interesting is that to see? We now have s times f of s minus f of 0 from the left-hand side. But when we think about the deviation of this effect and what's really happening here, we are going to be considering what's happening on the left-hand side as, I'm going to use a different color for this real quick. Let's consider the deviation of this term, where this deviation can become f of 0 on the left-hand side is equal to f of 0 on the left-hand side minus f of s. But we know that the deviation on the left-hand side of 0 is equal to 0. So we know that this actual term is equal to this term. So in reality, we are actually able to describe this very directly as s times f of s minus f of the steady state of whatever that initial value would be. So when we think about this and what's really happening, we've previously now described a step function where the step function looked like this, where if we had t equals 0, and this is going to be f, maybe our initial value, steady state, and our new value, and it went like this. And we were describing what's happening on the left-hand side and on the right-hand side based on this step change up for f. Here we are saying that on the left-hand side, this had to have been equal to the steady state value that we are presently using based on the deviation. So when we're really thinking deeply about what's happening here at 0 positive and at 0 negative, we are having some type of conditional value and change. But this is now looking into what's really happening based on a derivative operator for your function. So what's really happening as it starts to change and move as its output value. And it's really interesting that we can start to describe these equations in this way based on ultimately what could be our steady state values that we've plugged in directly. So we were able to solve the Laplace on a derivative function, and there's many other types of functions that could be present. So there's impulse functions, which would look kind of like this, where it might be at this steady state value, and then all of a sudden impulses up and it goes right back down. So there's just a singular moment when it actually goes up. And at that point, what's happening on the right-hand side and the left-hand side is that steady state value. But at exactly t equals 0, that is a quick impulse to just jump right on up. And we can also start to describe those types of functions as the impulse using Laplace. Using the solutions that we just have here, we can go back to resolving this differential equation for the heated stir tank. let's go ahead and rewrite this, but let's remember a couple of key things before we do. Ti for this type of deviation is going to be equal to 0. This is because there's no changes happening in our disturbance variable. T deviating at t equals 0 is equal to 0. That's because we knew that there was nothing happening until that step point was provided by Q. Additionally, we're going to describe Q now as our delta Q, which we already know is the actual amount or amplitude by which Q changes, and multiply that by its step function. We're just going to call that del T. So this is going to be the actual change by step, indicating that we have a step function based approach, determining how much of the change is present here. And this is going to be a simple value that just allows us to solve directly for what that step function is going to become. There's a lot of ways to write that, but I'm going to write it as this. So let's rearrange and put things back into our expression. T of dt equals Ti minus T plus kpq. Ti in this case is going to become 0. We're going to knock that out. We're going to replace Q by this functional form here, and we're going to be able to rewrite this now as T dt equals negative T plus Kp del Q gamma T. You can think of it as a delta T, you can think of it as a gamma T, whatever way is best for you. It could really be any function that you want. So just choosing your random one here. Now in this sense, we essentially have a new expression for our term. We're going to go ahead and cluster our temperatures on the same side because they're the same type of variable, and we're going to have tau dt plus T is equal to Kp delta Q gamma T. What if we now were able to solve this directly using a Laplace transform? We can take a forward Laplace into the Laplace space itself and then ultimately go back with an inverse Laplace to get the final solution. And now for something that's more simple like this, it might just be easier to go ahead and do the type of operations we were doing before, but you're going to see that getting comfortable with Laplace space is going to be a really fun way to solve really complex equations much faster. Especially when you have lots of different controllers involved, it'll be much simpler to do. So let's consider this on both the left-hand side and the right-hand side. So let's take the left-hand side, and I'll grab a new marker. The left-hand side of this is going to be Laplace of tau dt plus T. Now remember, this can be based on a linear expression. So we can take these two terms to be independent and solve Laplace on both of them. So this will be Laplace of tau dt plus the Laplace of T. We can pull tau out of the first part of the expression, and we'd have Laplace of this derivative function. Now we know what that derivative function is, and we can replace f now with t. So directly, that would become s times t of s, and this is still going to be in the functional space here, based on our deviations. In this case now, it's going to be minus t of 0 from the left-hand side. But t from the left-hand side at 0 is the same as t of 0, so this entire term becomes 0. Where that becomes that function. Plus the Laplace of t itself, well, in reality, that just is the function itself. Thus, that becomes t of s. On the right-hand side, though, we are going to have some different pieces that are actually going to become constant. So the Laplace of Kp delta Q gamma T is equal to, we can pull out these constant terms, Kp delta Q, and our step function. And we actually just did our step function in the previous example, and we saw that that's actually just 1 over s. So 1 over s. We can combine the two sides of our equation directly, and I'm going to switch to a new color for the combination of the left-hand and the right-hand side expression coming back in. And thus, using these pieces, we can go ahead and make this turn into t s t of s minus 0 plus t of s equals kp delta q over s. And now we can actually solve directly for t of s as a function of s. So let's combine the t of s's on one side and put the s term on the other side. So to do that, we're going to go ahead and cluster these, and it'll become t of s times tau s plus 1 equals kp delta q over s. We can divide by that term, getting tau of s is equal to kp delta q over s times tau s plus 1. And this yields our expression shown here. Now, one good goal to have is to actually get s on its own. So we are going to ultimately try and divide everything on this side by 1 over tau. That's going to allow us to get t of s is equal to kp delta q over 1 over tau for both is going to end up becoming tau multiplied by, now, 1 over s times s plus 1 over tau. Just by our division points out to take out the 1 over tau term entirely. And now you may notice I have tried to turn these into one part that's fully constant and one part that's still a function of s, where this constant term is present here outside, and on the inside we have 1 over s times s plus 1 over tau. A little messy, but I think we get the idea. Now, we can actually use some of our previous examples and even our tables that are shown in and do an inverse-based operation here, and ultimately what we're going to be able to find is a new solution. So really, when we take this inverse space here, we are going to be able to get, based on this inverse Laplace transform of t over s, is going to turn that into t of t, which is going to be equal to kp delta q over tau, which is good. And from there, we're going to be able to solve and essentially get this side of the equation directly. But that's going to end up becoming tau times 1 minus e to negative t over tau. So that'll become kp delta q over tau, is what we pulled out from the expression, multiplied by tau 1 minus e to the negative t over tau. Our tau's cancel, and ultimately we get back the same expression that we had before using our tables to get t of t, in this case, is equal to kp delta q 1 minus e to the negative t over tau. Now, this involved a Laplace inverse function that goes from our table directly, but we will still yield the same example as shown. And notice I multiplied by tau itself. It's truly more like 1 over the tau, because we have this 1 over tau term here, but I went ahead and just multiplied. Instead of doing 1 over, it's the same as 1. Just like when we consider our time function here, where this is mass over time, that becomes 1 over time, or time. But that is now kind of like an inception of time, because we're talking about doing 1 over of this tau, where tau is 1 over of time. So it's a lot to just say time. But we will be able to yield back our same expression as before. And while it may seem a little complicated to do this because this may be new math to some people, which is totally fine, one thing to remember is that this allows you to be using tables where you can pull things out directly and you can describe these functions in what would be a more simple ODE, now for more complex ODEs that we'll be approaching in this course. So I hope that was fun and informative to describe how we can look into the step function changes, where that was based on the step function operation that we chose for q of t with its amplitude. Now, if it's a different function, we can change that to an impulse or lots of different things that we'll explore in this class. But for this specific example, it was a step function that describes how q functions and is deviating based on the amplitude change between the two values. So I hope that was fun, and I will see you all next time.